Hi guys! Salamat sa inyong patuloy na ginagawang pagsubaybay dito sa ating discussions about mechanics of deformable bodies. At ang ating magiging topic ngayon guys is all about axial deformations and how these axial deformations may affect the position of a point or a joint of a truss that is subjected to a load. And here is our problem guys. The truss shown in the figure is pin connected at the joints and is supported by a hinge at point A and a roller at point B. Find the stress developed in each member of the truss and the horizontal and vertical components of the movement of point B when the modulus of elasticity of the truss is equal to 200 GPa and have the following cross-sectional area. The cross-sectional area of member AB is 400 square millimeter. The cross-sectional area of member BC is 350 square millimeter. And that of the cross-sectional area of the member AC is 300 square millimeter. So here is our truss guys. And the truss is subjected to a load of 75 kilonewton. Okay, there is a hinge support at A and a roller support at C. The dimension of the truss is given such that the member AB is 4 meters, member BC is 3 meters, while this member AC is 5 meters. And you would note that the truss actually is a right triangle because you have here a 3, 4, 5 triangle. So let us try to identify here what are our given. So we're given the following. The cross-sectional area or the modulus of elasticity of the members, which is equal to 200 GPa. The area of the member AB, that is equivalent to 400 square millimeter. The area of the member BC, that is equivalent to 350 square millimeter. And the area of member AC, that is equal to 300 square millimeter. So because of this triangular truss, we would expect that this angle of the triangle may be assigned an angle alpha whose function can be identified from the dimension. As such, we can say that the sine of this angle alpha will be equal to the ratio of the opposite side to the hypotenuse of the triangle, and that is equal to 3/5, which when simplified into a decimal value, that is equivalent to 0.6. Similarly, the cosine of that angle will be equal to the ratio of the adjacent side to the hypotenuse of the triangle, and that value is equal to 4/5, which when converted into decimal, that is equivalent to 0.8. We're going to consider this as our angle beta. Then this beta could also be expressed in terms of its function, so that the function of that angle beta will be equal to the opposite to the hypotenuse, which is equal to 4/5, while the cosine of that angle will be the ratio of the adjacent side to the hypotenuse, and that is equal to 3/5 is 1. So after we have identified the function of those angles, we can isolate joint B as FBD in order for us to determine the force acting on member AB and member BC. So if we're going to show it here, that would be the direction of our force. The magnitude is equal to P of AB, and this force would be inclined with respect to the horizontal, that is equal to the angle alpha. This angle is equal to angle alpha. Similarly, this member BC will be exerting a force upon the joint, and we will be calling that as P of BC. The direction of that P of BC can be shown here as equal to the angle beta with respect to the horizontal. Okay, knowing this angle alpha and beta, we can therefore solve for the value of PAB and P of BC by applying the condition of equilibrium, so that we are going to sum up force horizontal equal to 0, and assuming that the force directed to the right will be positive, therefore our equation will become equal to the horizontal component of AB, that is equal to P of AB cosine of angle alpha, minus the horizontal component of BC, that is equal to P of BC cosine of beta will be equal to 0. So that if you are going to substitute cosine of angle alpha, which is already taken as 4/5, and cosine of angle beta, which is equal to 3/5 in this equation, therefore our equation becomes equal to P of AB multiplied by 4/5 minus P of BC multiplied by 3/5 is equal to 0. Hence, we can say that P of AB will be equal to 3/4 P of BC. And let us call that this equation is our equation 1. Similarly, from this isolated view, joint B, we can apply the other condition of equilibrium so that we will be applying summation of force vertical equal to 0, and then considering that force directed upward will be positive, therefore our equation will become equal to the vertical component of AB, that is equal to P of AB sine of angle alpha, plus the vertical component of BC, which is equal to P of BC sine of angle beta, minus that value of 75 will be equal to 0. If we're going to substitute the value of sine of alpha and sine of beta, which are equal to 3/5 and 4/5 respectively, hence the equation will be reduced to P of AB multiplied by 3/5 plus P of BC multiplied by 4/5 minus 75 will be equal to 0. Now if you are going to substitute the value of AB, which is equal to 3/4 of P of BC, in the equation above, therefore our equation becomes equal to 3/4 of P of BC, which is equal to that P of AB, multiplied by 3/5 plus P of BC multiplied by 4/5 minus 75 is equal to 0. Now simplifying this equation, we shall be able to solve for P of BC, that is equal to 60 kilonewton, and because the direction of P of BC is directed towards the joint, therefore P of BC is subjected to compression. Now substituting the value of this P of BC in the equation for P of AB, then we can solve for P of AB, which is equal to 3/4 of 60, and therefore P of AB is equal to 65 kilonewton. You will notice that P of AB is also subjected to compression, as AB here is directed towards the joint. Solving now for the force acting on member AC by isolating joint C as FBD, this joint. Now let us try to isolate that joint. Here is our joint C. Joint C is now subjected to the vertical reaction at point C. There is a force exerted by, and that magnitude is equal to 60. And due to this horizontal member AC, there will be a force that would be acting here, and the direction would be opposite the direction of the horizontal component of BC, and the value is equal to P of AC. This therefore will be making an angle of beta, as P of BC is also making an angle of beta with respect to the horizontal. Now if we wanted to solve for P of AC, therefore we apply the condition of equilibrium such that the summation of force horizontal is equal to 0. So that if we are going to consider that force directed to the right will be positive, then our equation will be equal to the horizontal component of BC minus P of AC will be equal to 0. Now if we are going to substitute that cosine of beta, which is equal to 3/5 in this equation, therefore our equation will become equal to P of AC being equal to P of BC cosine of angle beta, so that this will be equal to P of BC, which is already computed at 60, multiplied by cosine of beta, which is equal to 3/5 or 0.6. Therefore we can solve for P of AC, that is equivalent to 36 kilonewton, and because P of AC is directed away from the joint, therefore P of AC is subjected to tension. After we have computed for the magnitude of the axial force acting on each member of the truss, we can now compute for the deformation of each member. Knowing the formula that the deformation is equal to PL over AE, now if we are going to solve for the deformation of AB, therefore it will be equal to the PL over AE of the member AB. We're going to substitute this value. P of AB is equal to 45 kilonewton, and this is equivalent to 45,000 newton, this one. While the length is equivalent to 4 meter, that is equivalent to 4,000 millimeter. The area is given to be 400 square millimeter, and the modulus of elasticity, which is equal to 200 GPa, is also equivalent to 200,000 megapascal or 200,000 Newton per square millimeter. Now, if we're going to cancel the units, you will notice that Newton here will cancel as well as millimeter square will cancel. What will remain will be a unit of millimeter and whose value for the deformation of AB is equal to 2.25 millimeter. Now, for the member BC, the deformation of the member BC is equal to PL over AE of that member. And if you're going to substitute the value of the force of AB is given to be 60 kilonewton, and that is equivalent to 60,000 newton. The length of AB is 3 meters, and that is equivalent to 3,000 meters. We are given the area of 350 square millimeter, while the modulus of elasticity of 200 GPa, which is equivalent to 200,000 newton per square millimeter. Therefore, this deformation will be equal to 2.571 millimeter. And finally, for the deformation of AC, which is equal to PL over AE, substituting the value, we have a load of 36 kilonewton, that is 36,000 newton, multiplied by the length of 5,000 millimeter, the area of 300 square millimeter, and the modulus of elasticity of 200 GPa. Now, simplifying this, solving for the deformation of AC, AC will have a deformation of 3 millimeters. So what shall we do next? So after we have computed for the deformation, then we will try to find out how this position of B be moved. Yung kasi ang ating hinahanap dito, no, we'll be finding for the movement of B in terms of its horizontal and vertical components. For us to be able to imagine how B will be moving, then let us try to show it one by one and with some kind of animation. Let us try to imagine that we consider saving all this deformation. You have the deformation of AB of 2.25, the deformation of BC of 2.571, and that of deformation of AC of 3 millimeters. Knowing that AC is in compression, therefore it will be shortening. BC is also in compression, therefore BC will be shortened by this amount, while AC is subjected to tension, therefore there is an elongation of the member AC. Now let us try to go back this illustration and let us try to magnify that figure, and let us show that here is the magnified or enlarged truss so that we can show how B will be moving. For us to be able to imagine how B will move, so let us try to show the deformation one by one and show it on the figure. And this can be done by imagining that this a joint or pin be removed. Let us try to imagine that that pin is removed, and let us allow that the deformation to occur freely. Let us show it one by one. Let's start by showing how AC will be changing its dimension, and because AC will be elongated by 3 millimeter, let us try to imagine that AC be stretched. And as AC stretched, let us try to show that this BC be following as AC is stretched, and this is what will happen to this member AC. Member AC is stretched by this amount with exaggeration for the sake of discussion. Therefore, this dimension, the difference in dimension between opposition of the C from this point up to that point, will represent this deformation of AC, which is equivalent to 3 millimeter. That is our deformation. And you would notice that if this member AB will remain connected to the joint at C, therefore this B will be moving horizontally at the same amount equal to the deformation of AC. This value will also be equal to that deformation of AC. Now, after we have shown the movement of point B caused by the deformation or the elongation of AC, let us try to show the deformation caused on the other member. Because this member BC is subjected to compression, therefore we would expect that BC will be shortened by an amount of 2.571. Let us try to show that deformation here by imagining that that deformation is that magnitude. Here is now our deformation of BC, whose magnitude is 2.571. And let us imagine that that end after BC has shortened by an amount equal to 2.571 be called as point D. Similarly, let us try to imagine that this AB be shortened by an amount equal to that deformation of 2.25. Showing it here, let us try to animate that deformation. That would become our deformation. Let us show it again. That would become our deformation. And this deformation will be our deformation of the member AB, whose magnitude here is equal to 2.25. Imagining that this end be called as joint E. So ano ngayon ang nangyari dito? You will notice that point E and F are now separated. But in actual situation, they are not separated. Di ba? So ano lang gagawin natin? We have to rejoin them by twisting the members AE and CD in the same or in the opposite direction until they touches again. So if we will be rotating AE and CD in this direction, you would expect that they will be meeting again at this point. So this becomes our final position F. But because the deformation is so small, imagine that this is only about 2.25 millimeter for a total length of 4 meters here, and a deformation of 2.571 here for a total length of 4 meters. Hence, this value is so small. And because this value are small, then this arc EF and arc DF can be imagined to be a straight line, which is perpendicular to AB and BC respectively. So showing that perpendicular line, so we can now show the actual position of F, this F, when this arc length will now be imagined to be a straight line. Then this position now becomes the actual position of point F. And from here, we can now expect that this position will be our final position moving out from the initial position of B before the load is applied. While this position of F is the position of B when the load is applied. And our problem here is to find, how is this B moving, from this initial position to this final position. So this can be shown by imagining that we pass a vertical line through D here. So if we will be passing a vertical line through D at this point, and a horizontal line that will be passing through F, then we'll be forming a triangle. You will see that imagining that this intersection of the horizontal and vertical line be called as H, therefore we are forming here a right triangle FDH here. Similarly, if this angle originally is angle alpha, therefore this alpha can also be taken to be this angle. That angle will also be equal to angle alpha. As such, if this angle will be our angle beta, therefore this angle will also be equal to angle beta, which is also the same as the angle that this BC will be making with respect to the horizontal. Now looking at this triangle, you will see that this deformation would have a horizontal component equal to this magnitude. Let us imagine that this position, this intersection, be called as G. Therefore, from that illustration, we can find that the horizontal component of the movement of B is the difference between this length BG and the horizontal length FH. You will find that this BG and the horizontal FH will be the horizontal component of the movement of B. But what is this BG equal to? But BG, as you would see, will be equal to the sum of the two components. One is the deformation of this AC and the horizontal component of this deformation of BC, whose value is equal to deformation of BC multiplied by the cosine of the angle beta. Now, if you are going to substitute the value, the magnitude of the angle, the deformation of AC is equal to 3 millimeter. That is equal to 3 millimeters plus the deformation of BC, which is equal to 2.571 multiplied by the cosine of beta, that is equal to 0.6. Therefore, the magnitude or the distance BG will be equal to 6.3426 millimeter. Similarly, we can compute for this distance FD. You can solve for the distance FD, where the distance FD will be the sum of the two components. One is the magnitude of this distance, which is equal to the deformation of AB, plus this distance, which is equal to the component of this AC that is parallel to the direction of AB. And that component will be equal to the deformation of AB multiplied by sine of the angle beta. If you are going to substitute that, deformation of AB is equal to 2.25, the deformation of AC, which is equal to 3.0, and sine of beta, which is equal to 0.8. Therefore, our equation for FD will be equal to 2.25 plus 3 multiplied by 0.8, and that gives us a value equal to 4.65. So that after computing for this distance FD, we can now compute for the horizontal distance FH, which is equal to FD, cosine of the angle alpha, where FD is already computed to be 4.65, and cosine of alpha is equal to 0.8. Hence, this value will be equal to 4.65 multiplied by 0.8. That is equal to 3.72. And after you have computed for FH and BG, we can now say that the horizontal component of the movement of B will be the difference between BG and FH, and that is equal to the value of 6.3426 minus 3.72, that is equal to 2.6626 millimeter. However, we can also compute for the vertical component of this position or this movement of B, which in this particular illustration will be the sum of the following distances, this GD and that of DH. So that if we're going to write that here, the vertical component of the movement of B is the sum of GD and that of DH, where GD is equal to the vertical component of the deformation of BC, which is equal to the deformation of BC multiplied by sine of beta. That if we are going to substitute sine of beta, which is equal to 0.8, therefore we shall be getting a value of GD equal to 2.0568 millimeter. And this DH will be equal to the magnitude of FD multiplied by the sine of angle alpha. But sine of angle alpha is equal to 0.6. Hence, substituting the value of FD, that is equal to 4.65, the value of DH therefore is equal to 2.79. So after we have computed for the value of GD and DH, therefore the vertical component of the movement of B becomes equal to the sum of these values, and hence that is equal to 2.0568 plus 2.79, giving us a value of 5.4526 millimeter. I hope guys that you are able to follow the presentation that I have shown to you. Sana guys ay patuloy nyo akong subaybayan sa ating ginagawang discussions by subscribing to this channel, so that whenever I have new uploads, you will immediately be informed. Once again, thank you very much for watching.